the flow of water from a faucet, rapids flowing past rocks in an energetically flowing river, the pyroclastic flow in a volcano eruption, and the heat transfer in the very heart of nuclear reactors. These are all examples of a phenomenon called turbulence.
Turbulence is all around us, and yet it's usually invisible.
Simply wave your hand in front of your face, and you've created incalculably complex motions in the air, even if you can't see it. Turbulence is hidden in the sense that you can see the swirls and eddies on the surface of a flowing creek, but not the patterns of motion that lie beneath the surface. In simple terms, turbulence is a state of fluid flow that appears complex and chaotic. It contrasts with laminar flow, which occurs when a fluid flows in parallel layers with no disruption between those layers. Physicists may describe turbulence using the following features: irregularity, diffusivity, rotationality, and dissipation. One of the pioneers of turbulence research was Osborne Reynolds. He conducted a series of experiments surrounding the flow of water in pipes, studying the features of laminar and turbulent flow. His apparatus was very simple. It consisted of a long glass tank with an opening which fit a long hollow tube. This was then connected to an external tap, of which a thin stream of dye would be inserted. First, the water in the tank was allowed to be completely static. Then, the tap was opened, allowing both water and dye to be introduced into the mouthpiece. At low flow rates, the dye resembled a straight cylinder thread, and the whole system appeared motionless. But when the tap was opened further, the laminar flow broke up into eddies, which diffused along the cross-section of the fluid. Reynolds identified this as the transition point from laminar to turbulent flow. These experiments resulted in the ratio known today as the Reynolds number, quantifying the ratio of inertial forces to viscous forces within a fluid. The movement between areas of high and low velocity generates fluid friction, a factor in developing fluid flow. The Reynolds number is widely used in fluid dynamics and plays a key part in predicting flow patterns in different situations. Now, turbulence is considered unsolved, in the sense that we are unable to predict, in detail, how a fluid will move under any particular set of conditions. Regardless, turbulence factors into the design of much of our technology, from airplanes to pipelines, and helps predict important natural phenomena such as the weather and ocean currents. Turbulence is both an intrigue and a mystery, combining important parts of physics, mathematics, engineering, and computation in a phenomenon even the layperson can appreciate. If we became masters of this fascinating phenomenon of nature, our knowledge of science, mathematics, and technology may be free to move into new and futuristic directions. Thank you for watching.